In this video, we want to cover section 4.6, which is modeling with exponential functions. The first example we're going to do is a population growth model. The first question here is, a culture starts with 4,000 bacteria. After 30 minutes, the culture has 6,000 bacteria. And we want to find a function that models the number of bacteria after t hours. To do that, we use our population growth model, which is n of t is equal to n naught times e raised to the r over t. And then we can plug everything in. So this is 6,000 is equal to 4,000 times e raised to the r times 1/2, right? 6,000 is our final value. 4,000 is our initial value. R is the variable we're looking for here. And t, the number of hours, is in fact 1/2 because we said it took 30 minutes to get to 6,000 bacteria. So when we solve this, the first thing we want to do is divide by 4,000. If we do that, we get 3/2 is equal to r over 2. E raised to the r over 2. And then we take the natural log of both sides, so we get natural log of 3/2 is equal to the natural log of e raised to the r over 2, which is in fact just r over 2. So r is 2 times ln of 3 over 2, which is just 0.811. And we can plug all of that in to get our equation. N of t is equal to 4,000 times e raised to the 0.811t. After that, the next question here is, find the number of bacteria after 2 hours. Well, to do that, you just plug in 2 into your formula. So I get n of 2 is equal to 4,000 times e raised to the 0.811 times 2. Plug all that in, and we get 20,252 bacteria. We have a third question, or third part to this first question. And that is going to be, after how many hours will the bacteria double? Well, to solve this, we want to plug everything into our population growth model, which again is here. N of t is equal to n naught times e raised to the rt. And the numbers we want to plug in is the original equation, 4,000 times e raised to the 0.811t. But over on the left, we need to write 8,000, and that's because we want to know how long it takes for our population to double. So the population goes from 4,000 to 8,000. Divide by 4,000 on both sides, we get 2 is equal to e raised to the 0.811t. Take the natural log of both sides, and we get ln of 2 is equal to 0.811t, which is 0.855t equal to t when we divide by 0.811 on both sides. And that's it for our first question. Now we want to look at a question on radioactive decay. Here, we are told that the half-life of radium-226 is 1,600 years, and suppose we have a sample of 20 milligrams. For the first question, it says find a function m of t equal to m naught 2 raised to the negative t over h that models the mass remaining after t years. Well, for this, we just plug everything into that formula. And so that's m of t is equal to 20, because that's our initial size, times 2 raised to the negative t, that's our variable. And this h here is the half-life, which we were given is 1,600 in this first part up here. We were told it was 1,600 in the problem. So that's our formula. We're actually going to be asked to find a second formula, because there's really 2 ways to write out a formula of this type. And question B here is to find a function m of t equal to m naught times e raised to the negative rt that models the mass remaining after t years. Here, notice that this formula looks a lot like our population growth formula, except in radioactive decay, our value is decaying. It's getting less. It's decreasing. So our exponent is negative in this problem, but otherwise the formula is the same. Then, to solve that, we need to plug everything into our formula. And what can we plug in? Well, on our right side, we have 20 times e raised to the negative r times 1600. If we assume our t is 1600 years for this, well, what happens to the final value? Well, half-life says that the initial value is then halved. So our final value here is 10. And so our equation we're trying to solve is 10 is equal to 20 times e raised to the negative r times 1600. Where again, 1600 is the half-life, r is what we're trying to find. That's the only thing left that we need for this formula. 20 is our initial value, and 10 is our final value after 1600 years. So we divide by 20 on both sides, and we get 1/2 is equal to e raised to the negative r over r times 1600. Take the natural log of both sides here. We get ln of 1/2 is equal to negative r times 1600. Solve for r here, and we get 0.000433. Which we can plug everything back into our equation and get m of t is equal to 20 times e raised to the negative 0.000433 t. We have two more parts to this question. And the first one is, how much of the sample will remain after 5,000 years? To solve this, we want to plug everything into our formula, and we can pick whichever formula we want, but the first one that we worked with was easier here. So we have m of 5,000 is equal to 20 times 2 raised to the 5,000 over 1600. If we reduce everything here, this is 20 times 2 raised to the negative 50 over 16. Keep going to reduce, and we get 20 over 2 raised to the 25 over 8. Right, I just 50 over 16 reduces to 25 over 8. The negative exponent moves everything to the denominator. And this is, in fact, 2.2925. Our final question, our final part to number 2, which is, in fact, our final question for this section, is after how many years will only 15 milligrams remain? Well, for this one, we plug everything into our equation, right? So 15 milligrams is our final. This is equal to 20, which is our initial, times 2 raised to the negative t over 1600. That was just our formula that we found earlier in part A. Plug everything in here, and we plugged everything in, and we divide by 20 here, so it's 3 over 4 is equal to 2 raised to the negative t over 1600. Take the natural log of both sides, so we get ln of 3/4 is equal to ln of 2 raised to the negative t over 1600. So this right side is just negative t over 1600 times ln of 2. Solve for t here, and we get 664.06 years. And that is it for section 4.6.